So your work needs to indicate not just the intervals where f is increasing and decreasing given this graph of f prime, but it also needs to have full support. I'd like to show you how I chose to answer this. And I'm not saying that this is the best way, but what I am saying is that I know this way is correct and will work all of the time. So one thing I really like to do when I'm answering a question, no matter if I'm solving an equation in calculus or doing something else, I like to at least spell out what it is I'm trying to do. So think of this a little bit like in geometry where you have to cite a theorem and then do stuff with it. That's kind of what we're doing. So this is me the first time here saying, I know f is increasing when the first derivative of f is positive and decreasing when the first derivative of f is negative. So looking at the graph, the first derivative of f is above the x-axis on the interval from -5 to 13. And the first derivative of f prime, is below the x-axis on the interval from -8 to -5, and then 13 to 15 again, 2 intervals. So if you didn't think of all of those things, it may be okay, but definitely as this is practice, it's worth your time to make notes on that. Last comment on number 1, before we move on to the second one, is notice how those are all open intervals. Now you can correctly communicate with open and closed intervals, but if you make a mistake in terms of which is open and which is closed, you're gonna lose points on the exam. It is best, and by best I mean easiest to reproduce, most consistently correct, to just use open intervals when you're answering any question about an interval. So don't even worry about if it's closed or open, just mark everything open. Okay, switching back. All right, does everybody see the new problem? New problem came up, okay. Great, thanks for the feedback. So this new problem is pretty different from the other problem, and not just because of how the question is asked, but also because what the question is asking to do. And sorry, it's not real clear. So we have student work here. So a student read through this, thought about it, looked at the information they have, and said that the domain of, h is increasing on the interval from 0 to 2, and when x is bigger than or equal to 6. So what I'd like you to do is think about whether or not that student is correct while you're answering it. And in order to answer that question, you may need to do the problem yourself, you may not. That's going to be up to you and how you choose to do it. So the short answer is the student was not correct. But what I'd like to encourage you to keep doing, especially if you're struggling in calculus, is make this type of thing a habit. H of x is decreasing when h prime of x is negative. Make sure that's a thing that you're writing down, because that helps you not just answer the question, but the repetition helps you make sure you know what's going on. So I need to look at the table, which has h prime of x in it, and determine when h prime of x is negative. So it's positive on these intervals and negative on these intervals. That means h of x is decreasing on the intervals -1 to 3 and 5 to infinity. You honestly didn't have to do this part to say where h prime was positive, but when I was literally answering this question, I had to do that in order to figure out the intervals, but it really isn't part of the answer. Generally, I don't encourage you to do things that aren't part of the answer, but if it's part of your process, it's okay. Just know that any time you spend on that, you don't get back to do on more challenging questions that you may need to worry about later on. So I've got some more. And by some more, I mean one more. And this question is extremely difficult to finish. You should be able to do part of it at least. You should know how to start, let me rephrase. You should know how to start it at least and be able to do part of it. But in terms of finishing answering it, it's very difficult. So don't get frustrated. Know that sometimes it's just like that. You may have noticed this already when you take an assessment in calculus. Some of them are immediately clear to you what you need to do. Some of them you have to think about for a little while before you know what you need to do, and then you do it and you know you did it right. Some of them you think about for a while and you do it and you still don't know if it's right. And others of them, you really have no idea if what you're doing is correct or not. Those are all fine things. And honestly, given the same questions on a different day, you might end up with different results. Some of the things that felt easy might feel hard. Some of the things that feel hard may feel easy. It's interesting how different our brain works and processes sometimes. But I'm going to pause the recording here and definitely stop talking. And I'm going to give you not enough time to answer this question all the way. Okay, swapping over here is my work for that question. And in order to come to the answer of g of x is increasing on the interval from 3 to infinity, I did 4 things. First thing I did was the thing I've been emphasizing for a lot of these. As I said, g of x is increasing when g prime of x is positive. So that tells me, okay, to answer this question, what I need to do is determine when g prime of x is positive. So I went about that in a way you may not have expected. What I did was I determined first when g prime of x won't exist. So g prime of x won't exist when the denominator, f prime of x plus 8 equals 0, which is equivalent to saying f prime of x equals negative 8. So I was talking something about this thing here. So I looked at where g prime of x does not exist, and that may have surprised you because you may not have gone about it that way. I also looked at when g prime of x equals 0, which is when the numerator is 0. So that's going to be when x plus 5 quantity squared is 0, or x is negative 5. It's also going to be when f of x is 0, or x equals 3. And this one may be a little bit confusing to you. I'll let you know where it came from. So we're told in the text that f of x has an x-intercept at x equals 3. Because f of x has an x-intercept at x equals 3, f of 3 is 0. So I used the information I had about g prime specifically, to make a number line here where I kind of sorted out the sign of g prime. So g prime is negative from negative infinity to negative 5, negative from negative 5 to 3, and positive from 3 to infinity. Since it's positive from 3 to infinity, I knew that g of x is increasing on the interval from 3 to infinity. So let's talk about a few things. Let's talk about why I did number 2 and number 3. So there's a perfectly good reason why. And it recalls a little bit of recall from what we did earlier in the week. And number 2 and number 3 could be considered as me determining the critical values of g. So the critical values of g are values of x where g prime does not exist or equals 0. And you may be thinking to yourself or thought to yourself the whole time, well, why would we be interested in that? Well, what I want you to do is think about if you evaluate a function like g prime, there are only 4 possible outcomes. G prime of x could be a positive number. G prime of x could be a negative number. G prime of x could be 0. G prime of x could not exist. So when I do a critical value investigation, what I'm doing is I'm finding every single x value of g where, or of g prime, where the output does not exist, is undefined or something like that. That's what that means. Or is 0. That means literally every other single value of x in the domain of g is going to be either positive or negative. So finding these values of negative 5 and 3 allows me to say anything that's less than negative 5 is either positive or negative. Anything that's between negative 5 and 3 is positive or negative. Anything that's bigger than 3 is positive or negative. That's why we want to start out some type of an analysis like this by thinking about what are the critical values, because it allows us to say everything else is positive or negative. And determining positive and negative here is the truly difficult part of this question. So let's do that. Okay, let's first look at the interval from negative infinity to negative 5. Okay, so on this interval, I already said that g of x is, or decreasing because g prime of x is negative. Well, how did I know that? I knew that by looking at g prime of x, which again is the formula x plus 5 quantity squared times f of x divided by f prime of x plus 8. And figuring out, is this thing on this interval going to be positive or negative? So normally, a lot of you I know just look at the graph and say done and done. This is why your only understanding of how to do this can't be just look at the graph and be done. You need to be able to go further sometimes. So when you're looking at the graph, what you're doing is you're studying the graph for values that are less than negative 5, like negative 7, negative 8, negative 10. You're doing it all at once because it's pictured. So that's what we're going to do, is look at just one value, because one value has the same representation for every value. So if we look at g prime of -7, we've got -7 plus 5 quantity squared times f of -7 divided by f prime of -7 plus 8. And we're looking at this and thinking that's not super helpful. Like, sure, -7 plus 5 quantity squared is positive, but what about f of 7? And what about f prime of 7? And we can actually figure out f of -7's sign. We cannot figure out the value of f of -7. Likewise, we can actually figure out the value or the sign of f prime of -7. We cannot figure out the value of f prime of -7. So what are the signs? Well, if we look at f prime of -7, we know that f prime of -7 is positive. Why is it positive? Well, we know that f is increasing always, which tells us every value of f prime is positive. So if we're at -7 or -20 or 5, 10, 15, 7,000, f prime is always positive. So think about what happens. This is a positive number plus 8. That is always going to be positive. Okay, that's pretty good. You might have figured that out. It's the last part that I don't think you would have figured out because it really involves some diagonal thinking. So get your bishop hats on. To figure out why f prime of -7 is negative, what we need to do is think about what else we know about f. And we only know one other piece of information about f, and that's that f is increasing. Now that's what we already knew. We know that f of 3 is 0. So what that means when I put those together is f of 3 is 0. When I'm at f of -7, I need to be at a value less than 0. The only values less than 0 are negative values. So if you do a positive times a negative, the numerator is negative, and the denominator is positive, the whole thing is negative. Okay, let's repeat the exercise from -5 to 3. Now, I already told you we got the same result. But let's reiterate again why that's true. Okay, so 0 plus 5 quantity squared is positive because you're squaring a value. It's going to be positive. Why is f of 0 negative? The reason why f of 0 is negative is for two reasons. The first reason is f is increasing, and the second reason is f of 3 is 0. So if you're at 0 on the number line and you need to get to 3 on the number line, we know that f is below or negative. Same reasoning, f prime of 0 has to be positive. Why is f prime of 0 positive? Because f is increasing. So once again, I have a positive number times a negative number divided by a positive number, or putting that together, it's a negative number. How about for 3 to infinity? Well, we might look at something like g prime of 5. So again, we've got 5 plus 5 quantity squared, which I know is positive, and that's multiplying f of 5. And then I have f prime of 5 plus 8. So f prime of 5 plus 8 is positive again. How come? F prime of 5 is positive because f is increasing. So any value of x in f prime is positive. So I do a positive plus a positive, I get a positive. It's different though now when I'm at 5 because f of 5 is bigger than 3. Sorry, 5 is bigger than 3. So that means the value of f of 5 is bigger than the value of f of 3. And f of 3 is 0, which means f of 5 has to be positive. So that's why this last one is positive. And that's why I think this question is particularly difficult. And one of those reasons is because, I don't know if you've noticed this in class, we've been looking at math pretty much 5 different ways. So we haven't just been doing calculations and formulas. That's one thing we've been doing. But we've also been reading math and writing math, and we've been looking at tables, and we've been looking at graphs. And we have to get used to all of those different types of representations, not just for AP Calculus, but because future ways that you're going to use math, so not just math class in school, but like actual math, involves looking at numerical reasoning patterns in many different ways. And that's what we're trying to get used to. And that was kind of why I had you start out with sketches. But what I'm going to do is take what you've just done and turn it around a little bit. So I've given you 4 statements here. And notice how the prompt is still the same. So what I'm adding on is I'm saying, here are 4 statements, decide which of these 4 statements are true. And my suggestion, because you both did sketches and talked about sketches with your team, is probably that those sketches, good job me, those sketches may help you answer those questions true and false. So this was information that probably would have helped answering those true false questions. I'm sharing it with you now. Now, this is not the actual text of the extreme value theorem, but we don't actually need the exact text to work with the extreme value theorem. So it's enough, and I underlined continuous on purpose, just to know that the extreme value theorem says if I've got a continuous function or continuous function on an interval, either one's fine, that function is going to have, or I'm sorry, a continuous function on an interval, closed interval, that function must have a global or absolute highest point maximum and a global or absolute lowest point minimum. It's going to happen no matter what the function is, so long as the function is continuous on the interval. So you may have noticed that a lot of times on your assessments, you've got a review question. And that's because calculus keeps going back and revisiting previous topics. There's a reason why we wanted to have such a firm understanding of continuity and differentiability and all those types of things, because those are necessary to essentially do anything. Imagine if you had a job where you needed to, I don't know, hammer in some nails and you never had a hammer, or you couldn't figure out which end of the hammer you used to hammer in the nails. Like, I'm using the claw part and all I was doing is putting holes in the wall. I don't know what I'm doing wrong. Okay, you got to make sure you're armed correctly with the tools. So again, to recapitulate, not enough information is false. We knew that the function was continuous on a closed interval. Therefore, the extreme value theorem tells us we have to have a global or absolute maximum, and we have to have a global or absolute minimum. Now, this is not a guarantee for any function unless it's on a closed interval. More on that in a bit. And then the last one is the actual statement for the extreme value theorem. We're not going to worry about memorizing the exact text of the extreme value theorem because we won't use it in the same ways that we did for the intermediate value theorem and the mean value theorem and Rolle's theorem. We don't need it for those types of things. We can get around it with a little bit less formal of an understanding, so we'll give ourselves a break. So in my mind, the confusing part is not there's a value C, because we're used to that again from the IVT, MVT, and Rolle's theorem. It's also not this idea of closed interval. It's this statement right here, such that f of C is greater than or equal to f of x for all x in the interval. What does that mean in some type of a comprehensible fashion? Okay, and what I've done is drawn you some pictures that may help you. So we've got a continuous function, it's a line, and at this value right here, because it's an increasing function, at this c value, f of c is this y value. Check out how f of c is larger than every other y value for every other point on the closed interval, right? F of c is bigger than all of these. Okay. Check out the next picture I drew, which might have been similar to one of the pictures you've drawn. So it's this thing right here, right? This point right here, the y value, f of c, is higher than every other y value for every other point. So like if I choose this point here, the y value is here, which is definitely lower. If I choose this point here, the y value here is lower. Even if I get close, all of these y values are lower. So this is what it means to say f of c is greater than or equal to f of x. It's a short way, it's a notational way of saying this is bigger. Same thing here for this last one. The c value right here has a function value, a y value. The place on the y-axis for this point is bigger than the place for the y-axis on every other point on here. And what the extreme value theorem tells us is it's not just true for f of c bigger than or equal to f of x, it's also true for f of c less than or equal to f of x. So just do a quick look and notice how that's true. There's going to be a point that's lower than every other point. So this text right here, f of c bigger than or equal, I'm sorry, this notation right here, f of c bigger than or equal to f of x, could be thought of like this. There's a largest y value. And not just there's a largest y value, there's a point. With a largest y value. Okay? So a quick note on why the function needs to be continuous. Here are some examples of functions that are not continuous. So if I chose an interval here that has a vertical asymptote in it, this part of the function and this part of the function increase without bound. They're going way, way, way off the paper. There is no highest point. There's a lowest point, sure, but there's no highest point. And then I got the special one I cooked up in the laboratory. Check out this one. So if I've got an open point here, here, and here, this function on this interval, it's not continuous and it doesn't have a highest point and it doesn't have a lowest point. How about that? That's why the function has to be continuous for the extreme value theorem to be true. Now, a final quick note on the extreme value theorem before we start applying this a little bit. This is just like the other three theorems. If the function isn't continuous, that doesn't mean there are no absolute maximum or absolute minimum. Just like for the mean value theorem, that doesn't mean there are no points where the instantaneous rate of change equals the average rate of change. It just means there may not be. So be really careful if you're looking at one of those theorems and you find the conditions of the theorem to be false. It doesn't mean the whole statement is false. It just means that it might be false. So be really careful with those theorems to make sure that you know what the alternative is. So if the theorem isn't true, what's the alternative? Definitely something worth clarifying with me, Mr. Lepkowski. So let's take a look at some practice. This is more a review of what we've done earlier in the week than using the extreme value theorem. That'll come later in the second part of class because of technical issues that you were here for. But I'll stop complaining about those and just say we're going to find the relative extrema for f of x equals 5x to the fourth minus 20x squared. All right, so that's what we're going to do. So what I think is really helpful, again, is to write down thoughts. If you're finding relative extrema, what are the things you want to be thinking about? What is the calculus and math you want to be doing? Maybe you don't want to write down everything because that would get too long, but at least writing down a few ideas is going to help. So here are a few of those ideas. The first thing is, I don't have a graph, so I'm going to be using the first derivative test. So what I'd want to do is download into my brain from wherever it else is in the back of my brain to the front of my brain to say, oh, the first derivative test. That was when the sign change of the first derivative happens. I've got a relative maximum or minimum depending on the pattern it happens in. So if the sign changes from positive to negative, we've got a relative maximum. If the sign changes in the first derivative from negative to positive, we've got a relative or local minimum. Okay? And kind of what we talked about earlier today, if you're doing that, then you want to be thinking about critical values because what you're concerned with is the sign of the derivative. So if you're looking at relative extrema for a function, you want to start off with critical values because that's going to allow you to determine the sign of the first derivative, and then you can apply the first derivative test. So we should get the first derivative here. Now, before we get the first derivative, and this is one of those math things I keep talking about. It only matters when it matters. It doesn't matter here because the function is a polynomial. But it does matter to think about if this function may have values where it's not differentiable. So that's not going to happen in a polynomial, but it might happen in another type of function. So I know if I take the derivative of this, the derivative is continuous everywhere. So this first part for critical values isn't going to happen. But I don't want the algebra of what I'm about to do to confuse me from knowing that there's two criteria for critical values. It's when the first derivative doesn't exist or when the first derivative is 0. So even though I take the first derivative and I set the first derivative equal to 0, what I'm really thinking about is two things. I'm really thinking about when this is 0 and does not exist. That's what I'm really thinking about. Okay, so this function will equal 0, and I decided to factor when x is 0 or x is plus or minus the square root of 2. Hopefully you follow all of that. I actually factored everything. I said x squared minus 2 is x minus the square root of 2 and x plus the square root of 2, those quantities. But I didn't write it down because I was running out of space in my writing. Regardless, what we're interested in is not the critical values themselves, although that tells us where to look for sign changes. So I guess we're interested in them. I overstated my case. But what we're completely interested in is the sign of the first derivative everywhere, especially around those critical values. So for f prime of x, this function right here, I don't have a specific interval, so I know I'm going from negative infinity to infinity, and my three critical values of 0, negative root 2, and positive root 2 divides everything up into 4 intervals. So what I want to know is for each of those 4 intervals, if the derivative is positive or negative. So I could look at the graph. So you could look at 20x cubed minus 40x, look at the graph real quick and get the same thing. You could also choose some representative values on each interval, substitute them in here, and just think about the sign. So we don't care about what f prime of negative 10 is. What we care about is f prime of negative 10, negative or positive. So really quickly, I know it's negative because 20 times negative 10 is negative, and negative 10 squared minus 2 is positive. It's going to be a negative times a positive, okay? So a value between negative root 2 and 0, negative 1, is going to make 20 times x negative, and x squared minus 2 negative. A negative times a negative is positive. If I look at a value between 0 and root 2, like 1, it's going to be 20 times 1, which is positive, and 1 squared minus 2 is -1. That's negative. That's why this interval is negative. And last but not least, we have 100, which when multiplied by 20 is positive. And when you do 100 squared minus 2, also positive. So you don't have to do a number line. You don't have to evaluate the function like I did. But what you do need to do is arrive at these correct statements that this interval, the first derivative is negative. This interval, the first derivative is positive. This interval, negative. And this interval, positive again. All right? Because we can now look at these critical values and say, hey, I've got a relative minimum or relative maximum because I can analyze the sign change. So I'll start off with x equals -2. At x equals, -√2. At x equals -√2, the sign of f prime changes from, well, what is it before? It's negative. What is it after positive? So what does that make me think about? It makes me think about a decreasing function that's then increasing. So decreasing to increasing, relative minimum. Sign change from negative to positive, local minimum at -√2. Then we move on to 0. And we look at x equals 0. What's the sign of the first derivative doing? Well, it's changing again. But it's not changing the same way as at -√2. This time it's changing from positive to negative. When f prime changes from sign from positive to negative, f has a local maximum. And we have another sign change, this time at +√2. At +√2, the sign of f prime changes from negative to positive. So f has a local minimum at x equals +√2. Now the last thing I'll leave you with here, and I know you've still got more writing to do, but I'm just about done talking, is if I were doing this question on my own, what I probably would have done was I would have combined -√2 and +√2 in the same statement, because I noticed they had the same sign change and the same result. I chose not to do that here because I want you to have that repetition.